We are recording. Well, did you get the link? Yes. Did you print out chapter 1? Strike 1! That's -1 off your quarter average. Hey, if you are absent from class, you are responsible for what happens in class. You gotta find out from somebody. Okay, I'll give you a break this once. Okay, so the homework was supposed to go. Oh, I said, did you get the link I sent you?
Yeah, the link.
Then obviously you should print out chapter 1, right? Okay, anyway, everybody printed out chapter 1? Okay, let's see it. I don't really want to see it, you can put it away. So one of the 3 PCH classes every day gonna be recorded. So today, I guess this week it'll be you, because I always do the first one because if something goes wrong, I can do it in another class. Yeah? So then afterwards, I gotta figure out how to put the link on the site. Let's see how that works. Okay, today we study logic. Now remember what I told you yesterday? I have notes for you. All the notes are in there. You don't need to take notes. Maybe once in a while you can jot some notation down, but everything should be there. So what I want you to do is I want you to sit and listen and absorb. That's how you really learn math. Okay, so logic is the science of reasoning. And like I told you before, if you really want to learn mathematics, you got to be able to think logically. Now the building blocks of logic are these things called statements. Okay, and of course there's simple statements like the ball is red, the dog is brown, x is greater than 2, x is less than 2. Those are simple statements, yeah? But we're gonna look at some more complicated statements. Now if you look in your notes, the first one is called the universal statement. Now let me give you an example of a universal statement. For all real numbers, I don't know if it's going to be the same as the example you got there. X and y, x plus y quantity q is equal to x cubed plus 3x squared y plus 3xy squared plus y cubed. Weird. Why do you think we call this a universal statement? Well, just look at the first 2 words, for all. We're talking about all the real numbers. That's why we call it a universal statement. Okay? So now remember, well, I don't think I told you this yet, but the kind of logic that we're studying, we're just studying the easiest kind of logic. It's called 2-valued logic. Every statement is either true or false. There's no in between, true or false. Okay? Now, if you take upper level mathematics, there's other kinds of logic, like this thing called fuzzy logic. So every statement is not just true or false, it has a state somewhere between 0 and 1. You can kind of think of 0 as false and 1 as true, but then you're going to have statements that have a value of like 0.237. It's somewhere in between true and false, but it's closer to false. Now you might be thinking, well, what do you use that for? Well, you guys ever went to this country called Japan? And they have this thing called the bullet train. You guys ever rode on that? Who rode on that before? Okay, isn't it like super smooth, accelerating and decelerating? You know why? Because of fuzzy logic. So, but before you can understand fuzzy logic, where you have an infinite number of states, we have to understand 2-value logic, where every statement is either true or false. Now look at the form of a universal statement. For all real numbers x and y, x plus y quantity cubed is equal to x cubed plus 3x squared y plus 3x y squared plus y cubed. Now either the statement is true or false. There's no in between. In mathematics, that's kind of like the way it is. So what do you think? Is this statement true or false? Come on, we learned this in Algebra 2. X plus Y, quantity Q. Oh yeah, our teacher taught us that. In fact, some of you probably learned it in Algebra 1. True or false? Do we even have to think about that? That's... Okay, 50-50 shot, because you're going to get this on the quiz or the test. It's a 50-50 shot. What do you think? It's only 2 points, so it's either going to be, like on the quiz, 18 or 20 on the quiz. True or false? Somebody take a guess. Quack, redeem yourself.
True.
It's true. Oh my goodness. Oh boy. Okay, but see, mathematicians, we're kind of lazy. We don't like to write out all these words like that, so we symbolize, okay? So, let me symbolize the statement. For all yeah. That's how you symbolize it. You got to get used to the symbol. So you can probably guess, what does that mean? For all. Okay, for all. What the heck is this? X and Y. What is that? Is an element of. You've seen that before, right? Now what is the capital R with that thing on it? That's the set of real numbers. Okay, before we go any further, do we even know our sets at least? Okay, let's go back to kindergarten. This is preschool. Okay, what are the first numbers you ever learned? 1, 2, 3, dot, 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 right? In fact, you probably learned these when you were in the womb, right? Right, no, when you're in the womb, right, don't your parents talk to you when you're in the womb? Studies have shown that it helps if you talk to the fetus, you know. So 1, 2, 3. Some people say words, some people do numbers, okay? But what numbers are these? These are called natural numbers. Wait, some people are writing this up. Do you know that this is in the notes? This is in the notes. Everything is in the notes. Okay, so look in your notes. See, where is this in the notes? See Hana Boka writing this down. No, but it's in the notes. Okay, flip through the notes. Keep flipping. Oh, it's not in the notes. What? Oh, okay, it's not in the notes because I just assumed you guys would do this. So maybe you better write this down. Maybe you don't know. These are called the natural numbers. Capital N represents the set of natural numbers. And then, when you emerged from the womb, then didn't your parents teach you about zero? You know? Like when you're a baby. How old are you? 0, right? Because you didn't make 1 yet, so you're 0, right? You know what I'm talking about? Like if somebody asks you how old you are, what do you say? 17, because you're not 18 yet, right? Or are you 16, because you're not 17. So if you're a baby, you say 0, because you're not 1 yet. Oh. Okay, so what happens when you add 0 to this set? What set is this? This is called the whole numbers. Capital W is the set. And then, when you were like 1 year old, then you started to learn about negative numbers, right? Dot, 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 -2, -1, 0, 1, 2. Good thing this is on the video. Oh my gosh. This is preschool. What is the set of this? This is the set of integers. And what do we use for integers? Oh, darn it. The capital letter Z. Integers. Usually we put, I don't know, they put the extra thing line there. You don't have to. Okay, then, what do you call, oh my goodness. What do you call a number that can be written as a ratio of 2 integers? The rational numbers. Oh my goodness, maybe we have to, okay, let's go backwards. I'm just flabbergasted. What is the set of all the numbers that we know of? The complex numbers. That's the set of all the numbers we know of. Okay, before we go any further, what is a complex number? You learned this last year. It's a number that can be written in the form A plus BI. Did you guys learn this last year? This is called the real part. This is called the imaginary part. So the complex numbers, these are all the numbers we know of, okay? So the complex numbers can be divided into two disjoint subsets. You guys know what I mean when I say disjoint? They don't overlap, okay? The complex numbers are divided into two disjoint subsets, and what are they called? The real numbers and the imaginary numbers. Now, I don't think there is a capital letter for the set of imaginary numbers. It could be I, but I'm not really sure, so I'm just going to write imaginary. Now, the real numbers can be divided into two disjoint subsets, and they are the rational numbers. You guys, okay, a real number basically is any number that doesn't have I in it, right? Like the numbers that you used to, the numbers that you learned in kindergarten. So we got the rational numbers. How come we use Q for rational numbers? How come we don't use R? Because R is taken. That's why you don't name your two children the same name. You got the rational numbers. Do I have to spell it out for you? And then the irrational numbers. I don't think there's a capital letter for that one. Okay, and then under the rational numbers, then you have these. These are all subsets of the rational numbers. Now, is it all? I should have put, okay, next year I'll put it in notes for next year. Okay, because you have to know all the sets because I'm going to be using these things. Okay, that's going back to kindergarten or preschool. Okay, that's a sidebar. Okay, so here's the symbols. This is what you got to know. Okay, so for all, so x and y are elements of the real numbers. So real numbers x and y, and this. Okay, and we already determined this is true because we learned this in Algebra 2. Yeah? This is called a universal statement. Okay, now let's look at the other one. It's called an existential statement. Existential statement. Okay, let me give you an example of an existential statement. There exist integers, no, let's go, A and B such that pi is equal to A over B. There exist integers, there exists. Okay, what's the proper one? I had a D minus in English. There exists, because there's more than one, yeah? There you go. There exist integers A and B such that pi equals A over B. Now, why do you think they call this an existential statement? Look at the first two words. There exist.
Existence.
Wow, that's great. Okay? There exists. So, universal statement, we're talking about all. Existential statement, there exists. Now, what does that mean, there exists in mathematics? What do you think? Well, it could be all, though. There exists means there's at least one. Okay? There's at least one pair of integers A and B such that pi is equal to A over B. Okay, that's what this statement is. Now remember, every statement is either true or false. What do you think about this one? Are there integers A and B so that when I divide them I get pi? Oh my goodness. Somebody come up with something. Hanaoka, redeem yourself.
What's the question?
Is this statement true or false? It's a 50-50 shot. It is false, that is correct. Why is it false? Mr. Park, my teacher, I remember when I was in first grade, my teacher taught me pi is equal to 22 over 7. Anybody thinking that? No, pi is not, it's approximately 22 over 7. It is not equal to. Anyway, we all know pi, right? What is pi? Pi is equal to 3.141592653589793, and then it goes on without repeating, right? Those are 15 decimal places, right? Everybody knows at least 15, right? Goodness. Whereas 22/7, isn't that 3 and 1/7? And everybody knows that 1/7 is 1, 4, 2, 8, 5, 7, repeating, right? Wait. Okay, stop. Do we have to go back to kindergarten again?
No.
Do we know our fractional and decimal equivalents? Like when I say 1/4, you know that's 0.25, right? What about 1/5 is 0.2? 1/6, 0.16 repeating on the 6. 1/7, 0.142857, repeating. What about 1/8? 0.125, right? 1/9, 0.1 repeating. Do I even have to say 1/10? 0.1. Wait a minute, you guys don't know 1/7. There's something magical about 1. Okay, let's go back to preschool again. There's not enough room on the board because when I video, I only can use this like 2/3 of the board right here. Oh my goodness. Okay, look, let me teach you something. Maybe you guys didn't learn this in elementary school. 1/7 is 0.142857. We say that 1/7 is a cyclic number or cyclic. It's cyclic. Okay, now why? Okay, let me show you something. What is 2/7? Well, it's going to be 0.2855714 repeating. Okay, let me show you 3/7. 3/7 is 0.428571 repeating. You guys see a pattern? Or this, I'm just writing random things on the board? No, it's cycling. That's why they call it cyclic or cyclic. You get some of you like, what? Look, 142857. It's in the same order, but it starts with a different number. Look, 2/7. So the next, what's the next biggest number that starts? This one starts at 1, right? So the next biggest number is going to start with 2, right? So look, same order, 285714. It's just cycling. 3/7 is 0.428571. It just cycles. Okay, now after explaining all of that, tell me, what is 4/7 then? 0.5, because that's the next biggest one. So and then you just go 5, 7, 1, 4, 2, 8, repeating. This is not magic. This is stuff we learned in preschool. No, I have to do 5/7 and 6/7, so you got it.
You got it.
You sure? Woo! Woo! Okay, anyway, so this is 3 and 1/7. That's that. But this is the actual value of pi, corrected 15 decimal places, and you can see that you only get 2 decimal place accuracy. But you guys did learn about, your teacher told you that pi is approximately 22/7, right? Somewhere in your life. 22/7. When did you learn that? Tell me. Pre-algebra? 6th grade, 5th grade, what? Give me something to work with.
Television.
Okay, you don't speak already, because you missed the first day of school. Okay, so a lot of people, in fact, in the times of the Greeks, and they actually used radical 10 as an approximation for pi, but that wasn't very good, right? Because what is radical 10 approximately? Okay, redeem yourself, Kwak.
3 point.
Oh, I could have done that. 162, right? Wait a minute, oh. Anyway, can you see that it's kind of close, but not really, so that's why they got rid of that one. And then I forget who came up with the 22/7, but that's closer. But see, that's really not that good. And then the Chinese came into play. And then the Chinese came up with a better one. Anybody? I think Mr. Masunaga. Who had Mr. Masunaga? I think he taught you this. The Chinese one. Are you Chinese?
Yeah, part.
Anyway, the Chinese came up with this one. Pi is approximately, now when I write this on the board, you're going to say, oh yeah, now I remember. 355 over 113. The Chinese came up with that one. And now you can think, who can even remember something like that? Well, Mr. Masunaga, what did he tell you? Just remember the first 3 odd numbers. What are the first 3 odd numbers? 1, 3, 5. Right? 1, 1, 3, 3, 5, 5. Easy to remember. Now is that starting to ring a bell, Mr. Masunaga? See? 1, 1, 3, 3, 5, 5. Right there. So anybody have a calculator? Nobody have, do I have to walk to my desk?
Calculator.
Okay, somebody do this on your calculator, quick. What, the rest of you don't have calculator? What about those of you taking chemistry? This is the class, right? A lot of people are in chemistry. Don't you need a calculator for chemistry? Okay, Haruka, give me all the decimal places that it's showing. 3 point.
1415929.
That's all you got?
Yeah.
Okay, don't feel bad, that's good enough, okay? Anyway, look at that. You got 6 decimal place accuracy with this Chinese one. So the Chinese one is good. And it's easier to remember the 22/7, I think. Just remember see, look at all this stuff I gotta go back to preschool. Okay, what were we even talking about? We're so far off track. We don't know what's happening now. Okay, get rid of this. This is all preschool stuff. Woo-hoo! Okay, going back to an existential statement. There exist integers a and b such that pi equals a over b. This is false because now we know what kind of number is pi. It's irrational. If you can write a number as an integer over an integer, it's a rational number. That's why they call it a rational number. What's the root word? Ratio. It's a ratio of 2 integers. I'm afraid to even ask this, but 0.4, repeating. Is this a rational number or an irrational number? Well, you just got to ask yourself, can I write that as a ratio of 2 integers? Someone will go, I don't know. Well, let me tell you this. Anytime you have a repeating decimal, that's a rational number. Right? Didn't we learn that in like first grade around there? Anyway, 0.4 repeating, come on, is 4/9. Some of you going, what? Okay, let's go back. Okay, from now on, every time we go back, we gotta make, this is the going back box right there. Let's go back to preschool. Do you guys know? Like, come on. I mean, you know why? You guys probably didn't play with your calculator enough when you were in elementary school. That's what I did. 0.2 repeating, 2 9s. 0.4 repeating, 4 9s. I see a pattern. 0.5 repeating, 5 9s. I'm getting it. 0.3 repeating, 3 9s. Okay, that's 1/3. Duh! You guys know 0.3 repeating is 1/3, right? Did you guys know this pattern or not? Or this is like just... And then here's the 0.9 repeating, 9 9s. That's 1. 0.9 repeating is 1. It is. Do you guys realize that? Some of you, look, you're like, what? 0.9 repeating is 1. It is 1. It's exactly 1. I'm not teaching. Okay, some other patterns. What about this? What is 23 over 99? 0.23 repeating. Do you see a pattern here? What is 0.235 repeating? You can probably guess now, yeah? What is that? 235 over 99. I mean, not 99, 999. Do you see a pattern, or I'm just writing random numbers on the board? Did you guys learn this or not? Or this is like the first time you guys are seeing this? I'm afraid to ask. Okay, but what if they throw, okay, this is all stuff that you should have learned long ago. What about when you have, okay, let me give you something that's kind of different. 0.275, and only the 5 is repeating. How do you, okay, this is anytime you have a repeating decimal, it's a rational number. How do you find the fraction for that? Did your teacher show you that? I'm pretty sure it was in the Algebra 2 book. Mr. Rubash didn't go over that. Okay, but it doesn't matter because we learned this in preschool. Okay, does this look familiar? Okay, why do we call x this number? 0.25555, it goes on forever. Okay, therefore, 10x is equal to what? What happens if I multiply this number by 10? What do you get? All right, my back is getting sore standing like this. 2.55555 repeating. What do you think I'm going to do? It rhymes with subtract. You subtract, and then you get 9x is equal to 2.3, and then all the other stuff cancels out. So therefore, x is equal to 2.3 over 9, but then if you multiply top and bottom by 10, you get 23 over 90. Wow! That's how you change a repeating decimal to a fraction. You guys learned this, right? You know it. What is this? Come on, somewhere in your life you learned that. Okay. How many times this year am I going to have to draw that box? Probably every day. I think. Okay, so we established this is a false statement because pi is an irrational number. Okay, but so Mr. Park, you said mathematicians are lazy. They don't like to write out the words. Yeah, we don't. So we have symbols. So let me symbolize this. There you go. That's how you symbolize it. So this backwards capital E. Where have you seen this before, right? Somebody said they saw Eminem. Who's Eminem? Marshall Mathers. You guys know Eminem? Till I Collapse. You know what I'm talking about? Who knows Eminem? Nobody here knows Eminem. Who's Eminem? Go to your room. How can you not know Eminem? Oh, I'm 53 years old. I know Eminem. Okay, who knows Eminem? Okay, doesn't he have a symbol like this? Anyway, I remember somebody had an Eminem T-shirt once, and that symbol was on it. And then I kept saying, hey, there exists! There exists! And then, I don't know, he wasn't responding to that. Because look, there exists, that's what that is. But Eminem, that's like the symbol, part of his symbol. Maybe it's oh my God. Maybe. Anyway, you can probably guess this symbol is there exists. A and B are elements of the integers. See, capital Z is the integers. Okay, but now you know that. And you can probably guess that this symbol means such that, yo, Mr. Park, I got that. But then when you turn it around, it means something else. That's right. So if it's this way, this means is an element of, but when you flip it around, it means such that. You just gotta get used to it. And pi equals a over b. So this is how we symbolize. Okay, so these are two other statements, okay? So, because we're not going to be really working with simple statements a lot. So we have universal and existential statements. Any questions? Pretty easy, huh? Okay, now, the next thing we got to talk about is negation. I don't have a lot of room on the board. Okay. Now, I know you guys know how to negate simple statements. Okay, so here, normally, okay, in logic, we always call a statement P for some reason. Well, that's because P stands for proposition, okay? Okay, the negation of a statement is written like this. Not P. Yeah, that's a tilde. But when we see this, you can read this, the negation of P, or we simply say not P. You guys know what negation means. It's kind of like opposite. That's why it's kind of like a negative sign. You know what I mean? This is like 3, -3. But statements are not positive or negative, so that's why statements have negations. But it's kind of like the same thing, it's the opposite. You guys know what I'm talking about? So let's make a chart over here. Let's look at some simple statements. If you have x equals 2, what would be the negation of that? I think you guys can figure this out. Or maybe not. X is not equal to 2. That's the negation of it. It's everything that's not equal to 2. Oh, okay. X is greater than 2. What is the negation? What are the numbers that are not greater than 2? Are you serious? X is less than or equal to 2. That's the negation. X is less than 2. What would be the negation of that? What are the numbers that are not less than 2? The numbers that are greater than or equal to 2. So that's how you negate simple statements. Okay, but now we have to be able to negate universal and existential statements. Okay, this is definitely in the notes now. Okay, so where am I going to write it? Okay, before we even go further, I want you to notice that every universal statement has a certain form. Every existential statement has a certain form. So every universal statement has the form. Where should I write it? Like it looks like this: for all box, comma, triangle. Now boil it, make it simple for you. Right? For all box, comma, triangle. Every universal statement looks like that. Every existential has the same form also. There exists box such that triangle. See? There exists box such that triangle. Okay, because maybe, see, and that's the beauty of symbolic logic. See, when we use symbols, we don't have to rely on the meaning of the words anymore. We just look at the form. That's the beauty of symbolic logic. Okay, because if you think about it as just form, it's really easy to negate. So, if we call this statement P, P is this universal statement. To negate it, you just got to do this. Okay, I'll just write it up here. Plus, this is in your notes. Okay, if this is statement P, to negate it, all you have to do is do this. There exists box such that not triangle. Wait, how come you guys are taking notes on that? Isn't that like written? There, negation, look at negation, right there. Okay, so here we go. So what would be the negation of this universal statement? For all real numbers x and y, this. Look, follow the form. There exists box such that not triangle. Now, this is triangle. What's the negation of gorilla equal banana? Gorilla not equal to banana. Period. There you go. That's how you negate a universal statement. So what is the negation of a universal statement? It's an existential statement. If you think about it, right? If somebody told you, okay, for all real numbers x and y, this is true, what would it take to prove that person wrong? If somebody said, all the real numbers x and y, that's true, what would it take to prove that person wrong? Don't you just need one counterexample? And doesn't there exist mean at least one? Right? So it only makes sense that the negation of a universal is going to be existential. And same thing over here. Same thing here. We call it, okay, let's call this statement Q. How do you negate an existential statement, but the negation of a universal is existential? What do you think the negation of an existential is going to be? A universal. So you just follow the form. It's going to be for all box, comma, not triangle. It's so easy. Okay, so here. See, it doesn't matter of the words we don't care about the meaning of the words, we just look at the form. Here's an existential statement. How do I negate it? You do this. For all box, comma, not triangle. What's the negation of pi is equal to a over b? Pi is not equal to a over b. And boom, that's how you negate. So if this is statement Q, this would be not Q, the negation of it. You guys get it? So tonight's homework, if you look at your homework page, there's two things you gotta do in tonight's homework. The first part is, I'm gonna give you either a universal or an existential statement. You have to write its negation. But it's easy, if you just follow the form that I just taught you here, that's easy. And then probably the hardest part for you is, you have to state whether the original statement is either true or false. Because that part, you gotta know some math. Now, I don't expect you to know this. Let me look at it. Who has it up? Right here. Okay. You don't have to know a whole bunch of math, but you gotta know at least some math. Okay, let me give you an example of tonight's homework. Okay, this is problem 0. For all real numbers x and y, cosine x plus y is equal to cosine x plus cosine y. Okay, so the first thing you gotta do is write the negation. What kind of statement is this? Universal. So we know the negation of a universal is very existential, right? So follow the form. There exists box such that not triangle. So if this is triangle, what's not triangle? What's the negation of gorilla equals banana? Gorilla not equal banana. It's simple. My dog can do this. Right? You see this, you do that. Can't be simpler than that. Okay, now you have to state, is the original statement true or false? Now you gotta at least know some math. But on the quiz or test, see on the quiz, the determining whether it's true or false is only gonna be worth one point, and on the test it's only 2. So you're not gonna lose that much. Okay, look at this. If I take any two real numbers, is cosine of quantity x plus y just cosine x plus cosine y? Yeah, Mr. Park, we learned that when we studied trig, but I don't really remember it. That's right, you probably really don't remember it, but at least you know that can you just distribute the cosine? No, that's ridiculous, right? So you know that the original statement is false. Even though you might not remember what the correct identity is, right? You know what I'm talking about? Although, to make this correct, what would it be? Cosine of x plus y is cosine x cosine y minus sine x sine y. Does that look familiar? Yeah. But I can't remember that. Yeah, I'm not expecting you to remember it, but I'm expecting you to know that it's not that. You know what I mean? You can't just distribute it. Just like this. If I have a plus b squared, can I just distribute the square? If math was only that easy. In fact, what about this? What if you, natural log a plus b? Can I just distribute the natural log? Natural log a plus natural log b? No! In fact, a distributive property only works when you have like a number on the outside, right? Like what about this? If you have 2 times a plus b, can I go 2a plus 2b? Yes, that's the only time the distributive property works. You can't distribute. If only math were that easy, everybody would get A's. Okay, so you know what I'm talking about? So everybody can do 1 through 10. Okay, now notice some of them I wrote in words, some of them I put in symbols. So you have to get used to it. Now, when you write your answer, I don't care if it's in words or symbols as long as it's correct. Now, the thing is, see, when you take a quiz or test, if you make up your own stuff, that's when you're going to get in trouble. So, like for example, take like your homework. You don't have it, I know. Look at number 7. Prime numbers. Is there a set of prime numbers? Capital P. Can I use capital P for the set of prime numbers? Well, every year there's always a few clowns that do. Okay, no, there is no such thing. So, you see, if you make up your own and you wrote capital P for the set of prime numbers, I would have to take out like 4 on the test. Okay? So, if you're unsure of what to do, then just write out it in words, right? Because, right, that's safe. You know what I'm talking about? Okay, the last thing we gotta do, what is this number 11 through 60? Notice all the answers are on the bottom, right? It says construct the truth table. What the heck is that? Well, I'm gonna show you. A truth table basically just tells you all the different truth values for a certain statement. Okay, I'll show you. This is the simplest truth table. If you have a statement, this is the negation of that statement, or simply not P. Okay, now remember, in logic, the kinds of logic that we were studying, every statement is either true or false. Like that, true or false. That's all. There's no in between that. So if statement P is true, what do you think about its negation? It's going to be false because it's the opposite of it, right? And if statement P is false, what do you think about its negation? It's going to be true. There you go. That's an example of a truth table. This is the simplest of all the truth tables. You guys understand how that works, right? Okay, now, what happens when you have 2 statements, P and Q? How many different, if each statement is either true or false, how many possibilities are there? Okay, how many of you took SAT prep? Okay, then you guys learned the multiplication principle. Oh boy, how many took pre-algebra? Then you learned the multiplication principle. How many outcomes does P have? How many choices? 2, it's either true or false. What about Q? 2, it's either true or false. So how many total possibilities are there? 2 times 2, 4. That's why they call it the multiplication principle. Wait, some of you are going, what are you talking about? Okay, okay, let's say you have 2 different hats. That doesn't even look like a hat. You have 2 different hats to wear and 3 different shorts. This is dumb. And then, but you got 4 shirts. Am I really showing this on the board? If an outfit consists of a hat, 1 shirt, and 1 shorts, how many different outfits can you make? This is the kind you get on the SAT. Well, how many different hats are there? How many different shirts? No, 4. How many different shorts? What do you think I'm going to do with these numbers? You multiply them because it's called the multiplication principle. So you multiply them to get 24. So there's 24 different outfits. Okay, you've seen this before, right? Oh boy, I can't believe I had to draw a box now. Okay, so same thing here. P, there's 2 choices, right? True or false. Q, got true or false, so 2 times 2, 4. Okay, now the standard way of doing this is, watch this. True, true, false, false. True, false, true, false. This is the standard way of making a truth table when you have 2 statements. Okay, that shows all 4 possibilities. Okay, now the 2 that we're going to look at today are this one, P or Q. You see the symbol? That symbol means or. Or we call this the disjunction of P and Q. Disjunction means or. Now the or statement is true. So basically what you gotta do is you gotta learn these rules. Okay? But these are rules that you guys already learned, in your mathematical career, but you're just not making the connection yet, okay? An or statement is true when at least one of the 2 components is true. So this is what you do. You go like this. Is at least one of them true? Yeah, so it's true. Is at least one of them true? Yes. Is at least one of them true? Yes. Is at least one of them true? No, so it's false. So that's what the truth table looks like for or. Get it? And then you can probably guess, what does this mean? And, which is the conjunction of P and Q. So disjunction means or, conjunction means and. Yeah, you gotta know that, okay? Here, this is this is how we learn it on the math team. Disjunction means or. Conjunction means and. See how disjunction or. There's no way you can forget that now. Okay, anyway, an and statement is true when both components are true. Okay, so you look at the 2 components. Are both of them true? Yeah, so it's true. Are both of them true? No. Are both of them true? Are you my mother? No. So that's all you gotta know. This is what you gotta do for tonight's homework. Okay? But then of course, okay, once we learn the basics, then you gotta extend. Okay? Does everybody understand this? This is all in the notes, right? Okay, so I'm gonna ask you, construct the truth table. I'm just gonna make up a statement. Construct the truth table for P and not Q, or not P or not Q. There. Construct the truth table for this more complicated statement. Okay, so how do we do that? Well, notice that there's only P and Q, right? So how many lines are there going to be in this truth table? 4, because there's 4 possibilities. So if you want to, you don't have to do this because after a while some of you are going to get good at it. You can start visualizing already, right? So this is like I'll put double lines. So this is like the training wheels here, P and Q. Okay, and remember what I told you? What is P? True, true, false, false. Q is true, false, true, false. Now, usually on the first few, you're probably going to put the training wheels, okay? So, this is how you do it. Okay, now, like I said, you don't have to show all the work. I'm basically just looking at the result, yeah? So, we know P is true, true, false, false. Okay, now, Q is true, false, so what do you think not Q is going to be? False, true, false, true. Not Q means the opposite of Q, so it's going to be false, true, false, true. And then I have to put these 2 statements together with and. When is the and statement true again? When both of them are true. So are both of them true? Are both of them true? Yes. Are both of them true? No. Are you my mother? No. So would you agree that this column here represents that statement there? Yeah, but then now we're going to deal with this statement. Okay, well, if P is true, true, false, false, what do you think not P is? False, false, true, true, because it's the opposite of this. Q is true, false, not Q is going to be false, true, true. See, now you can think, see, this is good to do on folder paper because you get the lines, yeah? Okay, now, I have these two statements. They are connected by or. When is the or statement going to be true? When at least one of them is true. So, is at least one of them true? No. At least one of them true? Are you my mother? Are you my mother? Yes. So, this here represents that statement there. But now we have to connect these two statements with or. So you have to take this and connect them with or. And when is the or statement true again? When at least one of them is true. So, is at least one of them true? No. Are you my mother? Yes. Are you my mother? Yes. Are you my mother? Yes. So this is the column that represents the entire statement. So we want to signify that. So usually we double box with an asterisk. Now, it's up to you. You don't have to put the training wheels here. Some people, after a while, they get so good, they just figure it out. And they write that down, and they go, write that down, and then they just look at these two, get that. And then after a while, some people are so good, they just visualize and go, and then they just write that. Now, right now, it's kind of hard to some of you going, how do you do that? Well, you have to practice. So after you do a lot of these problems, then I have no doubt some of you can just look at this and just go, but if you cannot, don't worry about it. Right? Use training wheels. What's wrong with training wheels? Okay, and then the last thing, Mr. Park, look at the last problem, or the last two. What? Now, when you do your homework, remember I told you, you got to learn from your homework. Homework that's where you do all the learning. Don't just do the homework and I'm finished. You got to learn from it. And that's something I'm going to have to teach you along the way. Look for things. Look for patterns and things like that. What happens when, are you guys looking at the last two homework problems? What do you notice about it? Got three, got P, Q, and R now. Oh, so when you have training wheels like this, if you are going to put the training wheels in, how many lines are there going to be in this truth table? What? What? I'm hearing everything except the correct answer. Multiplication principle. Every statement is either true or false. There's two possibilities. 2 times 2 times 2 is 8. I heard a 7 and a 9. I don't know where's that coming from. Okay, here's the standard way of showing all 8 possibilities. True, 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 false, 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 false. Okay, next column will be true, true, false, false, true, true, false, false. And then the last column, true, false, true, false, true, false, true, false. That's the training wheels if you have a statement with 3 different letters in it. You guys see the pattern now? So like, see, on the test, what happens when it gets extended? What happens when you have P, Q, R, P, Q, R, and S? 2 times 2 times 2 times 16! How do I fill it in? How do I make the training wheels, Mr. Park? Okay, let's just do it for funsies then. P, Q, R, S. What if? That's always something you gotta ask in this class. Because everything is always gonna go one level further. Okay, so what's the pattern here? The last column on the right is always alternating by 1. So it's gonna be true, false, 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 true. You wouldn't do that to us, would you, Mr. Park? Well, I don't know, but now that I showed you 4, then I gotta give you 5 now, right? But now that I said 5, now I'm gonna give 6. What do you think the next one is gonna be? It alternates by 2s. True, true, false, false, true, true, false, false, and so forth. Okay, what do you think the next one is? It's gonna alternate by 3. Who said 3? We're working with powers of 2 here. Thank you. True, 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 false, 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 and so forth. And then the last one on the left, what do you think? It's going to alternate by 8s. So you're going to have true, 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 false, 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 false. That's the pattern. Okay, now let me give you a hint. I think about 20 years ago, I gave this problem. This is a problem I gave 20 years ago. Who knows when you're going to see it again? P, Q, R, S, T, U, V, W, X, wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, what happens when you have 11 statements? There's no way I'm going to make you write out the whole thing because how many lines would there be? 2048, right? Look, 2 times 2 times 2 times 2, what is 2 to the 11th power? 2048, right? Okay, let's go. Here we go. Okay, I don't know, but I learned in preschool 2 to the 10th is 1024, right? I mean, that's just, no, you should learn certain things, like 2 to the 5th, you just know it's 32 already, right? So you know certain things, then you can use it, right? So if you know 2 to the 10th is 1024, then 2 to the 11th gotta be multiplied by 2, 2048, right? Okay, whatever. Okay, so, no, actually, you know what? I'm remembering the problem. I only gave 10. So how many lines would there be? 1024. Okay, so what I did is I said, complete the truth values in the 666th line. 666, I like that number. Not for the reason you're thinking of. What are the, okay, some of you go, what are you talking about? Okay, let's go back. Box. What are the first 7 prime numbers? Quick. 2, 3, 5, 7, 11, 13, 17. If you squared each of those first 7 prime numbers and you add them up, you know what you get? 666. Okay, anyway, in the 666th line, fill in the truth values. Because I'm not going to make you make the whole table. That's crazy for one problem, right? Would you be able to do this on a test? What do you mean, no, at least don't get all, okay, it's going to be 1 point for each one, so don't get a minus 10 here. At least get something, okay. You know in the very last column, it's going to alternate true, false, It alternates by ones, right? So if this is the 666th line, I think we can figure out that this one's going to be false, because all the odd ones are true and the even ones are false, right? At least you can get that one, right? And then you just figure out, okay, it's going to be true, two trues, 2 false, 2 true, 2 false, 2 true, 4 false. And then you can figure out where you are from there, right? And you just keep on going. Because this one's going to have 4 true, 4 false, 4 true, 4 false. Figure it out, right? Okay, what about the one on the left? You're going to have 512 true, and then you're going to have 512 false. Where does this one fall?
False.
False. This is bigger than 512. So yes, you can figure it out, right? It's just the ones in the middle are harder to figure out. I think I might give something like this. The last time I've seen this was like 20 years ago. Okay, we're done finally. I thought we were going to finish that. Okay, I hope this is right. I hope okay, let me just check this out. 289. Do you guys even know your square numbers? My teacher said you should know always your square numbers up to 25 at least. Okay, add them up. 18, 27, 28, 37, 37 plus 9 is 6. Oh, I think it's right. The last digit is 6. Okay, well, let's just do this for fun. Okay, 27, 36, 37, 46, carry a 4, 12, 18, 20, 26, carry on. Yep, it is. Thank you. Okay, we're done. So this class ends. Okay, now normally, well, it just depends on how many questions you guys ask. Normally, we finish class like 5, 10, 15 minutes early, and then you can start on your homework. But then, see, tomorrow, well, I guess not tomorrow, but on Thursday when you come to class, if you write a lot of problems on the board here, then it's going to take longer to discuss it. You know what I'm talking about? But then if I don't see anything here, then you're probably going to get lots of time at the end. Start your homework or whatever. Do your history paper. Okay, we're done. This class ends at 10:40, I believe, yeah? No! 10:45. How dare you? No, I don't know. Somebody help me out.
40.
Okay.
Maze restroom.
Okay, let me see if I can put